Hi, my name is Brian. Welcome to another video on derivatives. In this video, we're going to do an example for implicit differentiation. So our problem is the following. We have x y squared plus tangent y equals x plus y. So if you watched my introduction on implicit differentiation video, this was one of the examples I wrote down as an implicit function. And then I said I would take its derivative in another video. So here we go. We are supposed to find dy dx. Now when we start off this problem, I have to differentiate both sides. So I'm going to take the derivative of the left-hand side and then the derivative of the right-hand side, both with respect to x. So we have xy squared plus tangent of y, over here x plus y. So in the previous video I talked about how taking the derivative of y to the n is an extended power rule. I put it up right there. So you'll bring the n down, leave y alone, and then subtract 1 off the exponent. But notice that afterwards you have to then multiply by the derivative of y, which is dy dx. So anyways, when I am differentiating this, notice that this piece is a product rule between x and y squared. Next, this one is going to be a chain rule because I'll have to differentiate tangent first and leave y alone. And then over here we'll get to that. All right, so let's start with this piece. All right, so I have the product rule up there. We're going to call this f and then this one g. So that is going to be, I'm going to give myself enough room here. We're going to differentiate the x, leave the g function alone. Then I'll leave the f function alone, the x, and differentiate g. So it's the derivative of y squared. All right, now I'm going to do the chain rule, which I put the rule up there. We're going to differentiate tangent, which is going to be secant squared. You then have to leave the inside alone. And the chain rule then says you have to multiply by the derivative of the inside. Well, the derivative of y is just dy dx. Now on the right-hand side, when you differentiate the x, that's just 1. And then when you differentiate the y, that's going to give me dy dx. All right, so the derivative part is done. If I want to solve for dy dx, I need to get all the dy dx's on one side, everything else on the other, and then solve for dy dx like I was solving an equation. So these two, I haven't finished taking this derivative. So this is going to be derivative of x, that's just 1. So 1y squared. Then derivative of y squared is going to be 2y. And then multiply by the derivative of y, so that's dy dx. That's secant squared y dy dx. 1 plus dy dx. All right, so we have a couple dy dx's we need to get on the same side. So here, this y squared is going to go off to the right-hand side, and that's it. So these are going to stay, this and this one, and then this dy dx is going to have to come over as well. All right, so what we have now, I'm going to clean this up a little bit, call that 2xy. So we have 2xy dy dx. And then we'll have the secant squared y with dy dx. And then I have to subtract this single dy dx over. Then we'll have the equal sign. We have that 1. And then this y squared right here went over to the right-hand side. The next step is I want to get the dy dx's here. I'm going to factor them out. We'll have dy dx and then the stuff left inside. So that will be 2xy plus secant squared y minus 1. And that equals 1 minus y squared. Then the last step is to just take the inside right here, and I'm going to divide that over. So my final answer is going to be dy dx equals 1 minus y squared all over 2xy plus secant squared y minus 1. Anyways, that's it for our implicit differentiation example. I hope this helps. Good luck.